是我一个没证明，这个证明的吗？
对，
哦，
这个
local 的，
这个要证明。
好。
反正我那个因为那个它是那种医药国家，没有啊。
没关系，好，是有点，哎，他们这样太看不到嘛，啊。开始录影了，我开始录影了。Okay. Yeah. So in last class we talked about the optimization problem. Okay. Actually, today we have a lot of mathematics works. So I hope you can keep clear mind as well as myself. Okay. So we have a lot of mathematics issue to discuss to optimize your image processing approach. So this time, because we don't have enough time, so I remain this optimal notch filtering techniques to here, and we are going to show how we can optimize your filter to make the image process result better. So if you remember, we say optimal notch filter like this one. Oh, okay. Yeah. So look at this equation here. So it's optimal notch pass filter. So notch filter is you are going to specify any specific frequency component in your Fourier domain, and you are going to remove it. For example, like there's some sinusoid noise in frequency spectrum will become a pairwise spot. So you are going to remove it. However, if you look at the real world spectrum, you are going to remove part of it, and you will sacrifice a lot of different true image content. So we are going to say, you are going to do that one. Maybe you are going to look at every different location of the spectrum and give it the best weighting coefficient to remove it. So that's the way we're going to try. So first, you have to know the notch pass filter. So notch pass filter, you are going to find out a point filter of the noise, and see we just take this filter, notch pass filter, on your obtained image. Okay, G is the image degraded by your some active noise. Okay, so we just make a guess what kind of the noise itself. So you just take out the noise here, and it's noise spectrum. Okay, because your notch pass filter only filter out the noise spectrum, and so you want to look at the noise content. So you just take the inverse Fourier transform. So eta mm is your original supposed active noise from your observed image. Okay, so you have this eta mn, but we just mentioned maybe the area of this spot is contain a lot of your image content in a different location. So we want to say, okay, we are going to remove it, but only partial of it. So we times the weighting coefficient here, WMN here. So here is the key. We want to optimize our notch pass filter issue. So you can see it's your estimate image actually is become what did you do? So you just say, oh, it's observed image, and I'm going to remove the eta nn But we know the real world case, there are some different location in different your image area. So we say we are going to have some spatial coefficient, adaptive coefficient that can be changed depending on your image content, because your image content compared with the noise, they have different performance. So how can we find the optimal parameter at different location of this image? So that's the way we are going to do here. Try to find out a parameter W, and then we have an optimal solution to different location of this image, and then we perform like this restored approach. So here is the way we try to approach is usually try to minimize the variance at the specific location. So we consider neighborhood of this SXY. So we say we are always process this image with a sub image SXY or SAB. So we previously use SAB there. So you just define some small sub image and see what's the constant should be in this location. So we can write up this one, this equation here. So what's this? If you know, we are going to see the variation of this area image. We can calculate the variance, this one sigma square. So in probability, how you define the variance of the FSY at a specific point? You just take that value F specific value here minus the average of this sub-image, and then take square, and then take the average. So it's called variance, right? We know in the state probability we have two parameters. One is the average, the other one is the variance. So now we are looking at this variance of this sub-image. We hope this kind of restoration will become as stable as possible. So we try to minimize this issue. So where this one is the average of this sub-image. So we can see, we can write down this one. And this one, how to optimize this restoration by look at this W parameters. So in a small image, we try to simplify this issue. So we assume every sub-image, we take the constant weighting coefficient. Okay, so they can change in every sub-image, any different point you are going to look at. So at a specific area, here this W, we can assume it is a constant. So now we are going to derive after this assumption. Okay, so now let me define this problem again. So we have the noise in frequency domain, just like we say we have a notch pass filter on this observed image UV, right? So now we have this obtained noise like this one, and it's just inverse Fourier transform of this N UV. So it's just like an inverse transform of notch pass filter on your observed image. So this is the original eta you obtained. So after we obtain this one, we are going to look at how we do it estimate image here. So f of xy equal to what? You observe image minus, we are going to assume the previous approach. So our W is a weighting modulation function for your noise. So we are add up one more parameter here. So we want to optimize this one by selecting a good W coefficient, and then try to minimize the variance of this estimated image F hat. So try to minimize. So our problem become a new optimization problem by selection. Okay, so we can write optimize by selecting WSY. So let the variance become minimized. Variation of this f of hat, your estimate result is minimized. Within this sub-image. Okay, if you use some small image in this location, so your restoration problem is step by step in every sub-image without different W coefficient. is regarding to your image content and noise content. So we can write up this again. So we just mentioned try to minimize the variance of this estimated image in this sub-image. So you can write this issue again because it's the smallest. The minimized variance is we just calculate this one. So variation definition is every point in this sub-image, you define the size of the image, and then you estimate image minus the average. Okay, that's the variance, right? I think this basic probability. You want to evaluate the variance in this sub-image. You just take every pixel of your value minus the average in this sub-image and take square and then take the average. So it's a variance. So we try to minimize this one. And then based on your estimate image is have this coefficient. So let's just write down all the detail. So here I will skip all the detail here. So you can write what's the f hat, your estimate equation. So it is G minus W eta, right? So it's previous equation. We just have this estimation G minus W eta. Okay, and then minus what? Minus the average of this sub-image. So minus this average in this sub-image. So what's that? So you take the average of this equation here, this one, take average. So G, take the average, become G bar, right? So if we take the bar there, we represent it's an average in this sub area. And then minus what? W eta, average, right? So I missed this sub parenthesis. Okay, so minus this small area. So it's take the average of your estimated sub-image, and then we get this square. Square here, right? Without any change, we just take the definition of the average and definition of the variance. So we just say we are going to assume this in small sub-image, the weighting coefficient will become approximately constant. So what's the mean if we assume every small sub-image, the weighting coefficient the same, because you are going to process space sub-image. So you have to give a definition of the W you are going to select. So we assume W is approximately constant in SAB, in sub-image. So if it is constant, if you take the average, what's the result? It should be itself, right? So we can simplify again. So this is average of this one, and then write it again. G minus W eta, the same, and then minus, okay, minus what? G bar minus W eta bar squared. So we didn't change a lot. We just said we assume our weighting coefficient, ultimate parameter, is a constant in every sub-image. So it's some reasonable assumption. So we have a new equation here. So try to minimize this with respect to the W parameters. So how do? You are going to optimize certain function with respect to this W parameter. So what do? So in mathematics, we just take a, oh my goodness, what happened? Oh, don't tell me it's disappeared. Oh, good. Okay. So a few words disappear. That's fine. We try to assume this one is become. So we assume the W. Okay. Take the W is constant. Assume it's a constant. So what's the result here? Just take this one, and then this is the same, GW eta minus here square. Okay, minus this one, it's constant. The average, so it's a constant here. So that's a key issue here. So we can see here become constant. So it's third affect the average of the W eta products. So you can take the constant outside of the average. Okay, so we just mentioned you want to optimize. So what do you have to do? So you just take the derivative with respect to your parameters and assume it to 0. You can find the maximum result. Okay, so that's what our assumption. We want to, after your adaptive optimization issue, and then you can have a very stable and minimize the variance in every sub-image. So what do you do here? So it's just a very straightforward derivative operation. So let's see what's the result. Take the square. You can do that, right? Calculus. Okay, you pass the calculus. You know it's 1 sigma to W. So W is here, and it's a square. So what's the result? So it's the power of 2 will move to up the previous. So we have this one, right? Average, summation, and what's the result here? You just write down the equation once, and then derivative to the W separately. So we copy this one, G minus W eta minus G bar minus W eta average, and then this one times what? Times everything derivative to W. So what's that? Only 2 items have the W here. 2 items have W here, right? So you multiply what? Multiply minus W eta derivative to W. What's the result? Should be minus eta, right? Here for the first term. For the second term here is a negative, so it's positive. So it becomes add up eta average here. So it's just a second order derivative. Okay, so you can don't look at what I'm writing, just write by yourself. It's very straightforward derivative. So you can clear up all this detail here. So you can see, so it's a constant here. Just take an average. Okay, it's a take average. So we assume this is a constant. Okay, you can simplify this one. You don't have to rewrite it again. So what's this? So it's average. Try to average, right? K plus average, and this is the G minus W eta. So we write out everything here. Minus G bar plus W eta bar, and then this one multiply what? Multiply 2 terms minus eta plus eta average here, right? So please multiply 1 term by 1 term and take average again. You will see we will simplify this result. So let's write here. So it's equal to K average what? So it's G. So please help me to correct every process is right. So this time times this 2 terms. So it's plus G eta bar, and then minus eta W eta minus is become positive square, and become the next thing is the W eta bar. Next thing is the positive G bar eta. Next thing is the minus G bar eta bar, and next thing is the W eta minus. There's a negative there. W eta bar eta, and then plus W eta bar square. So you multiply out this one. Why I do this one? Because we are going to cancel out some terms. Why we can cancel out? Because all this process, there's some average process in front of this item. So please take the bar inside that one. If there's a no bar, so you take average, it's a constant already. Take the average again, it's also remain the same. But if you don't have the average process before, you have to add 1 bar there. So what's the result here? So the result will be minus G eta bar, right? This term, take the average. They multiply together, the sub-image, everything multiply together, take the average. So we get a bar together. So the bar separately a small bar and the long bar is different. So please make sure you can take the difference here. So look at this one. Take the average of sub-image becomes G bar times eta bar. Okay, so the bar is separate. Actually, this is the textbook didn't derive it. They just give you the result. So you try to validate the result here. So plus what? W eta square bar, right? For this term. This is already constant, so nothing affect for the average. But for the middle term, eta will become bar. So eta bar times eta bar become eta bar square. So it's a minus W eta bar square. And plus this one, G bar eta bar minus G bar eta bar because, eta. So it's the same, it doesn't change at all because it's already average. So there's nothing change. And then minus W bar, W eta bar square. And then plus W eta bar square because it's constant, no change at all. So you can see some term will be canceled out. For example, this one minus plus, this one plus minus. So there's only 4 terms left for this optimization process. So what's the result here? So you assume this because optimize effect after you have this derivative with respect to your parameter W. So what's the result here? So it's minus G eta bar plus G bar eta bar plus W eta square bar minus W eta bar square. Okay, equal to 0. So can you tell me what's the W there? Just sum up together. So it's from here you can derive W equal to what? Equal to, move to the right hand side. So it's a G eta bar minus G bar eta bar and W, so eta squared bar minus eta bar square. Okay, so go after so many mathematical, intuitive, straightforward process. You can just obtain this optimal parameter result for W. So every small sub-image you are going to process, and with your estimation of this restore notch pass filter result, you can come back to optimize your result. So we can see the example from the textbook. But how you do it? How you do it? The W coefficient at every XY, you have to do this operation from your observed image times sub-image times your eta notch pass filter sub-image. Then take the average minus sub-image of the G observed image times eta average, and then divided by eta square average and eta average square. So if you go back to look at your textbook, they just give you the result here. Okay, they say you can try to find out the one parameter, adaptive parameter W in every sub-image, and then please take this assumption, and you can get an optimized coefficient W in every different pixel according to your result here. Oh my goodness, what's that? Okay, so anyway, it's quite a straightforward derivative operation, mathematics operation here. So no worry, but okay, maybe it's also a process you have to run by yourself. Okay, we go through every detail there, but it's disappeared again. Sorry about that one. So maybe I will finish, continue finish this one after class. Okay, so that's the way you try to assume every sub-image can be predict, can be removed by some weighting coefficient, optimized weighting coefficient. So let's see what's the result here. Again, we can see if you choose the right parameter and every sub-image, okay, the W equal to what? W equal to G eta bar minus G bar eta bar divided by eta square bar and the minus square of the eta bar. So every point here, we are going to do that and see what's the result will be different. So the image of this Martian Terran taken by this spacecraft and Fourier spectrum like this one. So you can see, actually I can immediately obtain this the sub-image that like this a pattern noise, right? So you can just take, okay, here are some spot noise like. But unfortunately, part of this one is also a part of your original image. So if you just immediately remove all this one, maybe it's not as good as you wish the result. So, but we can do this one, optimize this one. We can do notch pass filter first. So you can assume this one and then get a eta first, eta mn from your assumption, and then notch pass. Take all this spot image. Okay, should be pairwise. Okay, if you take this one, you have to take the other pairwise one. Okay, remember? Okay, so it's if you want to do it, you have to do it pairwisely. Okay, so we just get this eta mn estimated noise from your spectrum, and then you will get this result. So this is the Fourier spectrum without shifting the. Okay, so this is another way. Another way you do it. So you can just say, oh, we'll keep all these low frequency part emitted it's easy way to keep the low content of your spectrum first, and you get this one like there's some spot noise there over there, and then this is your eta mm here, eta uv, and then get back to eta mn. So in spatial domain, if you assume your original active noise like this spectrum, like this noise in spatial domain, but if you move away this one, maybe a lot of image content itself will be removed as well. So how can we do? We just try to do this assumption. We are going to do our estimate is use f estimated minus w eta. Okay, so sorry g, and then do some assumption there. Okay, so you want to have some different w to optimize your restoration issue. So what's the result here? So what's this one? Yeah, this is we do this just previous optimization based on this assumption here, and then you have the eta nm, and you have the observed image. Actually, you can do this in every sub image you are passing through. So this is our result. Get this image. So it's not very roughly just take away use notch pass filter, but come back to optimize your solution and then make the image has the best output. Okay, so is that okay? It just gives. Actually, today we are going to have a lot of optimization problem issue here. Okay, later on we have some inner filter, we have some inverse filter, and how you pop up some combination, try to optimize your assumption on your filter design. Okay, so here is the first part of our restoration approach for additive noise only. So for additive noise only, but now we are going to consider also there are some filter. There are some motion filter, some different degradation model in your image first, and then have some additive noise or without additive noise. So we have three different conditions. One is no burn motion, only additive noise. The second one is combine both of them. The third one is no additive, only maybe only a motion blur noise there. So we are going to jump to the second slides here. Yeah. So actually, previous we have also introduced this image restoration with linear position invariant degradation function. So try to recall your memory. What's the linearity? What's the linearity? Okay, if it's non-linear, our work doesn't work. Our approach doesn't work at all. So linear is important. Linear contain two important characteristics of this degradation model. First is additive. So what's the additive characteristic of the system? And the second one is the homogeneity. So this is for linear characteristics. You have to satisfy both property as together. So additive is when you have a system. So if we have a system like this, okay, it's H, and this is your image F, and you have a output G. G is the F convolve H, right? So what's the additive of this one? So which means if you have the additive, you have a F1 into this system, you get G1, and you have a F2 image to this system, you have a G2 corresponding output. So activities, which means if you have a F1, we imply F2 together inside to this degradation model, you got G1 plus G2. So it's an additivity property. So what's the homogeneity? Homogeneity is scaling problem, scaling issue. So if you have a F like this one, is your degradation result of the G observed image. And the homogeneity is try to amplify your image. So it's which means if you have a F inside as your input image to this image to this degradation model, you got a multiplication of this the same scalar as well. Okay, so this homogeneity. Okay, you amplify a scale, and your output is the degradation model with amplified with a parameter. So in general, for these two, we have right A1 F1 plus A2 F2. We input this one, and we got A1 G1 plus A2 G2. So it's a linear model. Okay. So how about the position invariant? Actually, in time domain, we call it time shift, time invariant. Okay, for the speech signal, and for the image, we call it a position invariant, which means when you shifting your image in different position, the result degradation model will keep the same. They will not change their degradation result depend on your position. They only depend on your image content, not position. So, which means, for example, if your image system degraded in Taipei and you move to Kaohsiung, the degradation model still works the same. Okay, not because of your different attitude, the degradation model changed. So it's nothing related to your position of your image. It's only related to your image content or speech content. So we can say, if you want to say if this is position in invariant, we say it just for example, like if you use this kind of explain, you have a image or a signal in one dimensional. Okay, input this system, you get this degradation like a one square to triangle, and if you shifting your image, your signal to the right, and then through the same system, the result will become the same. If you shift t0 second, it will become t0 second. Okay, so it's just shifting. Okay, from center to right, from center to right. But the shape should be the same. The degraded, the filtering result, degradation model should be exactly the same. However, for the position invariant, which means if you, this is for invariant system. If it's changed, maybe go to this system, it become change different shape. It's position variant idea. Okay, so we have to assume these two basic degradation model characteristics is maintained in our system. It's a linear system. It's a position invariant system. So you have to make sure. So in mathematics, we will say position invariant. We'll say maybe you have a vector of H of f in 2 dimensions. X may be move some alpha position, and y move some beta position. Okay, so in your system, input is f, output g, and if you shifting in x direction, y direction with alpha beta position, the result will be g with x minus alpha and y minus beta, the same. So it's very easy, very straightforward to represent spatial invariant characteristics. Okay, so every discussion from this textbook, we are going to look at your degradation model is contain these 2 important property, linear, precision, invariant. And then we are going to talk about the inverse filter. Okay, if you don't have the additive noise, inverse filter will be the best if you know the model. And but if you don't know your model, there's some additive noise, you'll get this ester result because you magnify your noise in your result, restoring result. And the matrix formulation of the image illustration problem, we are going to discuss about that one, and we are going to tell you what's the constraint list square filtering. So we try to say we are going to have some constraint limitation and try to optimize, for example, like a winner filter and parametric winner filter. How can we find the suitable, like the previous we just demonstrate for optimal notch pass filter? You are going to find a parameter there, and the parameter can be changed, and then to find out the best restoration result by changing the parameter there. So it's a lot of mathematics here, and we have a different parameter setting, and it becomes a pseudo inverse filter. Pseudo inverse filter, and also we try to find out the winner filter in this class. Okay, so we mentioned all the linear and precision invariant degradation model here. So please remember all your standard image model there. So I remember we already discussed how do we find out this edge. So if you don't have a noise, and then you look at your image result, you obtain image result, sometimes you can try to think about what's the degradation model in your system. Okay, so there are some different way to find. The first way is using image observation. We have 3 different approach. Okay, so we have 3 different approach here. So identify portion of the upper image. So we have 3. The first one is use imaging observation. You just observe your obtained image and then try to see what kind of degradation model. The second one is just to do the experiment in experimental design. So which means you have your imaging system, how you get this your image, and then you just use some spike light source to go through to check your degradation model from your imaging system directly. So do the experiment. So one is try to observe, estimate. The third one is modeling. So you know the basic model of this kind of environment from mathematics. They publish a model, just use it and then modify some parameter to try to adapt your degradation model. So image observation. So you have to find out some sub-image, and then from this image, so maybe you are going to see some background, like our later on we'll see some image textbook, and you know their border, their constant background with some border, and then get that one, and you will see some blur motion, and then try to recover it. Okay, so this is very based on your experience, how you find out the sub-image, and then estimate one, and you observe one, and then try to estimate your original one. Is background, so it should be very simplified image content, just the background image with some border. Okay, so you just assume a kind of your original image should be, and then divide it by the opposite image spectrum divided by your assumed original image. You can roughly estimate your degradation model. Okay, so that is a very experience, based on your experience and based on your image. Is there any clear background model, and to assume that one. A second one is the experimental approach. So you have to use a point of source of light, and then try to use your image system here, and use a point of source of light here, and we call it a delta mm there. And then if your system here impulse response of this system is just take the convolution of mn combined with delta mn, and the convolution for any signal combined with the impulse function delta m become itself. So which means if you have an imaging system, just keep the light source in front of your imaging system, and then observe the result. The result is exactly your degradation model function. Okay, so it's the way. The only thing is you have this image system as your hand, and you can do that experiment. Okay, so why we have this like this observe is you observe spectrum divided by A, which means you have some different level of your light source. You can tune in your light level there. So maybe you have a delta mn there. So the delta m for this impulse function transform to this one become constant A here. So it becomes constant A in spectrum. So you have different tuning your different light source or light intensity level in your input light source, and then you will get different output of the constant value. So it divided by this one. So it's because you have done an adjustment in your light source. You scale up your light source, become very bright, okay. So you have a different output of in frequency domain. So in that way, so your frequency spectrum is very easy. You observe image, transform into Fourier domain, and then divide by the constant A, your light scale intensity. So you'll get this one. So this is the degradation estimation by impulse calculation. So A is the impulse of light, and B is the image degraded impulse. So you can see, actually I put this impulse into the imaging system, and I can observe the image immediately. And this one is exactly the HMN there. So this is the HMN. So later on, we have this log the HMN. We can go do some restoration issue. Okay, so if you know everything, if your real image input to your system, it become your observed image. So now you have this one, and how you estimate this one? Very easy. How you do that? You just transform into frequency domain. If there is no additive noise, okay, the assumption is there's no additive noise, and you will see your result, your restored image will become what? Your F hat. So you have reserved your this one, and you just get your observed image divided by HUV here, and you get this estimated, and then inverse transform, you get the restored image immediately. So HMN is the most important issue we are going to discuss. What's the HMN in your image system? So if you don't know it, try to observe, try to evaluate, try to experiment, and another one. And the last one is you don't know nothing, you just have this observed image at hand. But it comes from some special system, like this satellite image system, and they have a special model of the degradation model, like this one. So this is for the image for the degradation model for the atmospheric turbulence. So it's a satellite image system. You get this image from the satellite. Maybe you have this turbulence from this atmosphere. And also, this is the model. It looks like Gaussian model, actually. It's a Gaussian model degradation. And depending on the K is behind the environment. So you have to multiply the K to see is that the today's condition for the specific K. But for example, like cloudy system, the K is different. For a sunny system, the K is different. So you have to evaluate the K is a constant depending on the nature of the turbulence. So it's a different environment, you have different K to get a result. Actually, this looks like the Gaussian low-pass filter. Indeed, our atmospheric turbulence is some kind of Gaussian model, and with this different power, 5 divided by 6. Okay, so it's just the Gaussian look like low-pass filter. So you get this satellite image. There's some gradation already. So it's a Gaussian low-pass filter. So it's used to model this mild uniform burning technique. So you want to know what is HUV there. So we just tell you, if you have the model, previous experience model, you can do that one. So this is an example for this turbulence, atmospheric turbulence, the environmental illustration of this one. So if it is for a K is different from 0.0025. This is the smallest one. This is the smallest one. The second one, the largest one. So you get the image. So this is original without any turbulence model or neglectable image. So you can see the K different in different environment. You sometimes get this kind of image from your observed image, and you can expect how to find out this coefficient K there. So this is a three-way to see. The second example is the motion blur. So I think you have a lot of experience on this motion blur. So like people like me take the cell phone shot because I was handling what's that shaking hand. So I take the image and then I move my hand, and you will get this result, right? So it's a frequent result. If you move your image camera and take the image, oh, someone is moving, or your object is moving, walking, and you take your image with this shutter speed, and you will get this kind of result, right? So immediately, if you look at this one, try to see it's kind of motion blur because your object is moving or your hand is moving when you take the picture, take the shot, and then this we call this a motion blur. Actually, motion blur is like this kind of a model here. So it's very frequent occur in your daily life, and you take the image. Actually, this is just like this a model in degradation model in frequency domain spectrum. And why we can write up this sinusoid degradation model and times this exponential. So this is the way we have to introduce, because it's very, very popular one, and we have to look at this one, how we derive and get this one. So we can assume that T is the duration of the exposure. So it's really depending on your shutter speed. Okay, your camera shutter speed, and then during your taking the shot, the duration is the how many times you take this shot, and the exposure of your object. Either you moving your hand or your object is moving, you'll get this kind of result. And immediately you know what kind of direction the object is moving. Your hand is moving. Very clear, right? In negative 45 degree, right? In this direction. I already tell you the books look like this, and this is your result, observed result. So what's the kind of bird model? And you just look at when you take the picture, you move your camera in negative 45 degree. Okay, very clear. Is some straight, yeah. So that's what we say. If you have this some kind of background image here, and then you can try to expect. Look at this one. Try to expect what kind of degradation model. Okay, so if you have enough experience, you will make a good guess. But this one is very clear. It's a degradation model from motion blur function. So we are going to look at what is the motion blur. What's the motion blur function? So let's define this one. So it's especially if you didn't see the image, the degraded image shaking as well. So if it is kind of shaking, is very complicated. Let us assume your motion is linear in one direction. Okay, so you take a picture. Okay, or your object moving in a linear in a very short period of time, t seconds. So our assume is that uniform linear motion. Okay, so g of xy is what? Your exposure result, t second. So f is x minus like this one. So it should be very easy to explain. So it's a linear motion, right? Because your image, your G image is opposite image. Your F is your image, but it's a moving linear direction in t second. T is the exposure time. Okay, and the x0t, this function, and the y0t, you can expect what's this function? What's this function? Your linear speed, okay, in x direction and y direction. If you didn't move your hand in y direction, only in x direction, so you can see your degraded image should be in horizontal blur. If you only move in vertical direction, so y0t motion linear function is occur, and in x direction there's no blur effect. So it depends on which direction. If you both of them have occurred, so it's like the linear, the 45 degree in the right direction or 30 degree, whatever. So we can see if you take the Fourier transform of this one. It's pressed. So we will later we will see how to do this one. UV, and how can we obtain this kind of motion blur degradation function in Fourier domain? Try to find out the HUV there. So let's take 10 minutes rest and come back. And yeah, so we have a lot of mathematics to derive. Try to find out linear motion without to get this equation here in Fourier domain. Okay, yeah. So take a 10 minutes rest.这样还没有问题了哈，顺。
它好像放大，然后有时候它就会回
我会跳掉
复到上一个
放大，所以我不要放大。
发现是放大的时候，
我就真的不知道，我只是觉得我好像手碰到。好，没关系，这样对。homework 是下个礼拜吗？
对，下礼拜3。
我们有4个 homework， 最后一个在就是 winner filter。
好，
我 winner filter 有 example， 你有吗？
有
哈。好，那可能先想一个degraded image 吧。
好。
要 linear motion 的吗 ？linear motion 啊
？OK。
Lena 可以啊。
好。
给他加个 motion， 然后给他们，然后不用告诉他们让他们自己去试嘛。看看，试试看。
所以我就给 motion 之后。
再加 active noise。
哦。
这需要加 active noise， 那看看结果怎么样 ，SNR 就可以比了。
好。
好不好？简单，他有做，偶尔会给范例，他们就 follow 做就有分数。SNR 比较高的就分数高一点。我不知道有没有办法做那样。好，谢谢。
所以我要设计题目给老师看。
你试一个看看啊，好不好 ？Lena 试一个看看，应该还好了。
还好。
如果用拍下来才会有发现。就比如说它叫，我刚刚可以下载，比如说下载叫什么叉叉叉，点 B， 但是这个然后它是这样，它打开怎么样？多2个引号。 我用这个 i plus 网页下载。对，就是。这边进 到位也是情况会。都是前面的 daily 所以我们前面周。有笔电应该不会，还是没来，我没有印象，因为我通常都是用平板。我看一下，因为我是跟朋友买，他便宜卖了。因为觉得我的实力还是有放下的，然后他的消息很少看。你是最近才买的？没有，我是之前。而且我们中间没有3个，是吧？哦，你是买我是买笔记而已。那你们买多少钱？我跟我朋友买8000块。18000。这个买来完全没有用，因为我那时候刚出。他好像也是买18000。我这个不是，他用第二代，没有，我这不是 Apple， 那个是大牌的。你要请假的，他还不保，他们换系统，没有，他是单程这个。他那时候买是想说他玩游戏，然后用平板玩游戏比较好。我去年就报那个公益的补习班，就是想说大家上课都用平板，然后我都没有一台，平板卖我，然后说哎呀，卖你，意思说一个给你拿8000就好了。没有到很多那个差异，就是我那时候用基本那个笔电，然后大家都会看键盘，是你的贴膜吗？没有，是因为太红了。一样用这个。我那时候贴没那种，没有，他是单纯喜欢看，看手机。没有，我去买的时候，他手机也没有贴，他手机很不需要。我也觉得平板不需要。有来就我刮，他说你刮很多还是没有，那你要换，你要换，我是不有地方。10年我是2017，没钱币的嘛，很久，然后我觉得，所以现在人家这样说，然后换我觉得老师那样，这个应该就可以。但现在是公干，对，现在没什么很难啊。这个要买。可是我觉得，因为我现在有组了那个官方的线，然后这样搭起来是1套。如果要是整套换的话，我觉得快3万5，要买一台。那前提可以买一台。所以你在讲什么？又不懂，对不起。我是那需要那一代的。对啊，拿这个一代的。然后可是新的现在都是3个人交。没有。对啊，他1代我们在哪里？还有那个有一代。所以我想说，要换的话，那个换那个不如再等到我有钱。不知道你变的有没有说买更好的？他们这边没有在充电，学这个优惠。哦，对啊，你们说是明年暑假，对啊，他9月都会有那个 back to school。现在买那个1代手机，出一堆做那你们家现在不会学画？我是直接画贴片，好像我也觉得我就画画 所以说我现在这样，因为它的背景很板，然后只要放大的时候，然后我画一画，对，我想说现在这样，我想比较
你给你那部分，我以前你给你们这些最近就他对其实他这个也不是两个。可是他现在是买断是多少？600。900这么贵？我怎么好像买600？因为它说股神要用的话，那好像也蛮好的。是没什么兴趣。应该说会用到两个词。那我很想知道为什么不知道，我记得有时候写一写，然后压到还是我也不知道说换签名我这个都没有，没有原厂。他有一个蛮方便的。因为
我觉得2下，因为2下跟相当差。
看老师都。我拿你知道为什么我他可能手掌压到，我那个手是到，是他那个软件，这是关他那届的档案。再可能看一下他快捷键，
你说写一写就写，没有第一页。
对，然后那个就消失了。没有，在看一下，我在想哪里有开那个。这个好像很多人印象中，我觉得是要看一下他的个性，他的刚好触发到，所以他是没有人写在手机。他有时候像我这也是有时候跳回但东西因为我记得这里居然你是写一块下去之后，所以我觉得他是在背的时候，由回到上面，完成开档。没有啊，应该不会吧？他重新开档他会跳那个。我觉得有可能是软体吧。不要紧 ，refresh。我觉得比较有可能是软体，就是它正好这样子压到。下面这不给这全部是都是现在画一个然后没有间断，然后那个是消失，
那就地震压下去，它会它为什么会这么不知道？
受不了，买个 PS5。
没有正好，
死了，我买下去，我未来半年就
我买条超长的。
只要少。
就要喝那个。再买。蓝牙解锁器，可以研究我那时候无法
感觉我那时候用1本、3本、4本都会更容易输入那个，因为你他放飞歌。
被国政老师叫走了。好，来这里哈。好，继续，谢谢。Okay, so we have this motion assumption in different direction. Okay, x direction and y direction here. So let's try to do some Fourier transform and look at it in what's the result will happen. So see what's the definition of Fourier transform? It's a minus infinity to positive infinity. So all the spatial domain function times what Fourier transform is times exponential minus j to pi ux plus vy, and then dx dy, right? So it's a basic definition of Fourier transform. You multiply this kernel, okay, exponential to minus j to pi ux plus vy in two directions. Okay, so please put into your G observed image here due to the motion blur. Okay, so what do we have? We have this one, and then we have G of xy is 0 to t, f is a motion function, and y minus y 0 t motion function, and then derivative to t and dx. It's exponential minus j to pi ux plus vy dx dy. Right. So it's inside. You just put a g of xy here, and then to transform. So it's all the basic definition for this image, and look at it in Fourier domain. Now we are going to do a small trick. What do? We change the parameters, and then take the dt to outside of this xy dx dy. So this integral function process, the calculus will go outside, and inside we do first what? So it's become 0 to t, and then it's for xy derivative, and your function of x minus x0 t, y minus y0 t here, and it becomes dx times exponential minus j2 pi ux plus vy dx dy first, and then dt later. So you can see, because inside of this one, there's no t variable in this transform kernel. So the kernel can be moved inside there, and the dt can move out. So it's an independent function, so no effect. So let's just do this result. So what we do that? So if you look at this one, this is the Fourier transform. Okay, for a function, the function is shifted in x direction and y direction. So if you go back to check your Fourier transform lookup table, you know some spatial variation transform in Fourier transform process. It will become one extra term occur, and so this is outside remain the same, dt remain the same, but inside of this Fourier transform is a f function transform, but f is space shifted, so the result will be fuv. So if you check this Fourier transform lookup table, and then because they move shift in these two results, so they will times some transformed shifted result. So it's minus J2 pi U x0 t. So look at the table, transformation table, y0 t. So how you move? If you move A pixel, B pixel, they'll become A here, UA, and VB here. So it depends on how many pixel you shifted in spatial domain. So in frequent domain, your transformation is just add one more term here. So it's a dt here. So it's transformation result, just like this. Okay, so what's this? If you look at this transformation result, look at table, and you can see f of uv is in frequent domain, nothing related to the time variable. So it can move out. So f uv outside of this function, and then the inside. So it's a still guv result for the motion bird. Is posture time minus J2 pi U x0 t minus V y0 t here and dt. So you can see it's become a very straightforward problem. The GUV, because of the motion bird of the image, is moved, and it's become the original image free spectrum times this exponential exposure function there. So we only have to do is how to find this the result of this one. So let's add one more hash here. Okay, so let's write it clearly. GUV is become f of uv. Okay, times this exposure function, exponential minus J2 pi, and U x0 t minus V y0 t, okay, dt. Okay, so let's focus on this exposure function here. So try to simplify this one. Let's suppose we only motion blur in one direction, in x direction, y is different, but later on we will add back. So if we assume there's no motion in y direction, which means y0 t is 0. There's no motion blur in y direction. So let's simplify this one. Later on we will add it back. Okay, so it become what? And we assume if we linear, we have the same speed motion in x direction. So we assume what? Assume x0 t. Simplify this issue. So we can see the function of the motion in x direction is like this one. And what does this mean? It means if t equal to t, x0 t equal to a. So we just assume this linear motion in x direction. When you move in capital T second, and you move a pixels, a distance. So this is the linear motion function here. So we assume S0 t is AT divided by exposure time. It represent when your exposure time, your shutter speed, your open camera, your lens, and then your shutter speed is T second. And after that, your object moving a pixel, a distance. So that's a function, linear function here. So what's the result here? So let's suppose HUV. So here is a HUV, right? Here is a HUV. Because our observed image is an original image, FUV, times degraded function there, and in frequent domain. So this the later part is just the HUV, your degradation model. Or remember we say your observed image actually is the HF degradation in frequent domain, multiply your original image in frequent domain immediately. So actually the later part of the integration is just as the HUV, your degradation function in frequent domain. And in MATLAB, remember is you have to multiply pixel, corresponding pixel. So it's a matrix, two-dimension matrix. So in MATLAB, don't do right is multiply this one directly, okay? You'll get a wrong result. Why? Because 2D multiply 2D is in mathematics is column row-wise, multiple column-wise, and then sum up together, right? Okay, next example we will describe more. So in MATLAB, you have to write dot multiply. Dot is important. Dot is which represent in MATLAB environment. The 2x2 two-dimension matrix. Their product multiplication is applied corresponding pixel multiplication. This is what we do in image processing. We don't do this traditional row-wise multiply column-wise in matrix operation multiplication. Okay, so be careful. This is the right one. This is the wrong one in MATLAB. Okay. Anyway, there's a relationship between your input image spectrum times dot multiply your frequency domain spectrum and get the observed one. So what's this one? If you assume this under this assumption, not in y direction, only in x direction, horizontal direction moving, and it's h of uv become what? Become very simplified. 0 to t, exposure time, and exponential minus 2 pi times u, x0 t is t a t. Okay, dt. So just copy down this one, put into there. So what's the linear motion result? Is actually it's 0 to t, and you can see what's the result for this calculus integration. Can you do that one with respect to time value? So let me write down even better formula. Pi u t a t, okay, dt, okay. So the calculus from your mathematics calculus is a very fundamental integration of the exponential term, right? So this is the parameter in front of the small t variable. So which means, should I write this one? What's the result? It's 1 over e a x 0 to t, 0 to t, okay? Because I look some students' eyes with puzzle, okay? Curious. Okay, so it should be very simple way to do the integration, right? So it's a constant a here. So you just put this in your minus j 2 pi u a t e minus j 2 pi u a t t t and then t equal to t minus t equal to 0. T equal to 0 is 1. Okay, should be immediately, right? So let's put it into there. So yeah, is that okay? The t replaced by capital T and minus t replaced by 0. So replaced by capital T, replaced by 0, and you got this result. So what's the result? Put it right down again. So it's just copy down again. So maybe you can do by yourself, easier way. So it's minus j 2 pi u t a, and replace this small t by capital T here. So t cancel out. So it's 2 pi u a, capital T cancel out, and then minus 1. And so previous we still have this coefficient here. So sorry, I should put it here, the parakeet. So should be like this one. Okay, so here it should be the coefficient together, and then remain this one and replace t equal to t. Here is t equal to 0. Okay, so get a constant one. So what's the result? Actually, just let's simplify this one. If we have this 2 pi u a pi u a, sorry, I try to make a sinusoid pattern occurred pi u a, and t is upside down, and there's 2j minus 2j j2 here. Okay, in this content inside here, we can extract out the simple atom minus j pi ua. So what do you get? It's a minus j pi ua. This one should be minus positive j pi ua, right? So try to multiply this part, extract the similar component here. So if you just multiply inside, you'll be exactly the same. And let's add one more page. And here is okay. You have to know what's the sinusoid here. So sine theta equal to what? 2j exponential j theta minus j theta. Cosine theta is equal to 2j, 2, no j, e j theta plus e minus j theta. So this is the sinusoid in complex form. So you know what I try to do? Because this pattern, there's some e j theta minus e j minus j theta, and divided by 2j here. So if you have minus here, in positive, minus here, positive. So you can see this is a e j theta minus e minus j theta here. Okay, so this one divided by 2j becomes sine theta. So it's we have this rest constant here, pi ua. And this is becomes sine theta here. Sine what? Sine theta is pi ua here times e minus j pi ua here. So it's a HUV. HUV here from our exposure time definition and power linear motion definition, and we have this result for the HUV in frequent domain with the constant moving speed. Constant moving speed. Okay, so if you can see that one, we can in general, okay, we can come back to say also I have the motion linear motion in y direction. So in general, we can see. Oh, let's write a clear. Repeat this again. Okay. So let's summarize this. HUV is the result as t by divided by pi ua and sine pi ua times sine pi ua, and then times what? Times exponential minus j pi ua. But we say in general, we are not only moving in x direction, we also in y direction. So in general, our x0t, previous we defined linear motion in t second move a distance, and also y0t constantly linear motion with in exposure time capital T second and moving b pixel in y direction. So in general, like this one, so we say it can be exactly extended to this one, pi ua plus vb here. Okay, because you are going to move the y also in this the integration. So we have a sine pi ua plus vb here, and then we have this times this exponential minus j pi ua plus vb. Okay, so we can see it's just derived from immediately original your motion assumption, and it's a linear motion, and your assumption is this one, and you can derive this one. If you have it also in y direction, so you have this UAVB here, a pattern inside here. So please come back to look at this our previous original assumption here. So exactly the same. So if you know how the textbook write this one immediately, because we assume in y direction they have some in exposure time capital T second, they move b pixel, b distance. In x direction they move a distance. So we have this turn here. We have turn here, and we have this exponential item, and we also have this constant in front of this one. So it depends on your the level of your degradation model. It depends on this sinusoid, depend on this one, and depend on this one. So T is the duration of the exposure time, and A and V are displacement, the distance moving in capital T second. So we got this HUV. So how you get it? Actually, it's derived from this Fourier transform directly. Okay, from this directly Fourier definition, and from this exposure time, and from sinusoid definition, you get this result. Okay, I hope you can understand all the process. You can do is look at your Fourier transform lookup table. So the image has birth uniformly in linear operation here. So that's a result we got. HUV, the motion result, were like this. We have the example, right? Here's an example in T second. Okay. Okay. How? So let's see. Uniform linear. So this. Oh, yeah. Okay. I already typed in here. So please look at this one. So the result. Okay. So motion blur. So we have three different approach to evaluate your HUV. Evaluate your HUV. So please see which approach is suitable for your application. If you have an imaging system, use a point light source and impulse response. Look at the impulse response. If you don't have anything, just have the observed image. Try to find out the clear background model and with some edge location, and then to estimate. And then the third way is use mathematics models. You have to understand what kind of degradation model you are facing, so you can get a good result there. Okay, so now we know we have this degradation model already. So how we can process, how we can restore our image from this observed or the modified degradation model there. So the first is inverse filter. Okay, inverse filter. What's the inverse filter? It's just upside down of your HUV. So you see our estimate image. You can obtain directly using this division operation. So as long as you know HUV, take your observed image GUV in Fourier frequency domain, divide by this one. Okay, so it's directly applied inverse filter to this one. So we can write down like this, R times G. Okay, R is the inverse filter here. So upside down, divide inverse of your degradation model. We can rewrite this like this one. So it's just a mathematical writing, or your restoration of this R is just in type spatial domain is convolution. Okay, so it's not no big deal here. So in practice, we actually use a slightly modified filter. As long as you know H already, even you know there's no additive noise, but be careful. You are not going to divide without any limitation, and then perform this one. You ruin your image immediately. Okay, so why? Because I just tell you, all our image spectrum is from low frequency to high frequency, but your high frequency component is less energy. Okay, so if you divide it, maybe you have something wrong occur. So we have to do some protection. We just say if your HUV estimated or modeled or from mathematical models and it's very small, what will happen? See, look at this one. Look at this one. You use this inverse filter. So at every specific frequency component, if your HUV is very small, the value is very small. So 1 divided by very small value, what's the result? we will magnify this energy spectrum immediately. So you can imagine that there will be very disaster. So you just magnify everything at the higher frequency part. So that's the reason. So we have to do this one. Some constraint. HUV larger than some value, you can perform inverse filter. Otherwise, it will become zero. What does zero mean? If it's inverse filter is zero, here zero is, which means you are not going to do anything. It's output will be zero because inverse HUV inverse RUV is zero. RUV is zero times everything at less value. They are going to be nothing there. It's most, but it's not going to be disaster. So epsilon is a small value to avoid numerical problem when this is a small, because they will magnify the energy a lot. So the inverse filter work fine, provided there's no noise, it's fine, but it's illustrates still some reason there. So you don't know if there's any active noise in the process, anything in your low high frequency component. But if you just provide this directly, and you know HUV always our frequency domain always like this distribution in the high frequency domain is a very small value there, very small. When it's small, and then in the denominator, the effect will be a lot. So there's a way we say it's a small than some epsilon value. Don't do it. Okay, don't do the inverse operation. Otherwise, you'll magnify a lot. Especially if there's some active noise, it's a normal condition. We have some extra noise there, and the noise actually get amplified. Will be seriously amplified when HUV is zero, especially it's zero. Okay, or very small. Either condition, your image is not restored. It's destroyed immediately. So you can try, okay? And the contribution from the noise turn is everywhere, and you know it's like white noise. Everywhere you have some noise spectrum, white noise spectrum. And if you take the inverse of this value, especially when HUV is small, it will amplify it. So illustrate this one, we can see this example. Okay, even there's no noise or there's a noise, we can see the result. Okay, so inverse filtering, with no noise there. So you can see here is your filter. Okay, and your filter, this is just a uniform filter. Okay, it's all constant 1 divided by the size of your mask, and then this is the FMN. Okay, so let's see what's this result. So this is a GMN with this degradation. The different size of your degradation mask, N equal to 7, N equal to 11, and N equal to 15. 15 by 15, the mask. And then you can see the mean square error. Okay, because you have your original F image, so you can calculate mean square error. How you do it? It's a pixel wise, and your original location, intensity level minus estimate, recover, restored, predict, result, and then take square, and then sum up all the error together and take the average. Okay, so it's called mean square error. And the mean square error, when it's small, which means it is close to your original image. Okay, so we are going to take some degradation model first. Use uniform to degrade it. You know it must become blur, right? And if your size is larger, the blurred result will be even more serious. So you can see it's for size of 7 to deblur your image, to blur your image, and size of 11 to blur your image, and size of 15. So it's the mean square error become larger and larger. Okay, so when your degradation model mask size is larger for the uniform blurring, and the result can see it's more serious, and the mean square error is like become higher. The size larger is become higher, and we use this restoration. So we know this one, and you just take the Fourier transform and divide it, take the inverse of this Fourier transform, and then times your original observed image here. So this image transformed into frequency spectrum divided by HUV, and that's the result here. So you can see it's become larger there. Okay, so do we set up epsilon? Yeah, we set up epsilon there. If you didn't set up, it become a lot of worse result there. So you can see we set up epsilon as smaller than 0.001 when your H filter H of UV H of UV here Fourier transform to HUV, and then check this epsilon with this parameter setting. When it's smaller than this one, we are going to become 0. The inverse becomes 0. So there's no magnification for this spectrum value in an energy location. So the result like this. For the small one, get this MSE recovered, and this recovered image get this one, and this is the larger and larger. It's definitely because your degradation model is more serious, and you change do this degradation deblurring result, inverse filter result. You get pretty good result here. Here again, there's no noise. If there's no noise, and we use this kind of Butterworth low-pass filter, right? The Butterworth low-pass filter. Remember, there's different order. Okay, so this is the order 2n order there. So here maybe assume order is 1, and it's divided by your D0 is your cutoff frequency. This is cutoff frequency in frequency domain. Okay, we previously used D0. Okay, so it's D0. R0 is the radius, even the same. Okay, so it's a Butterworth filter. Butterworth filter, and R0 is a different radius. Okay, you know the Butterworth filter also similar to the Gaussian, similar to the uniform, but the radius is different. When you larger, your effect or your degradation result will be different. Okay, so you pass through this small radius Butterworth filter, only small energy remains. So it's become very serious degraded image. And if you remain more image from the Butterworth filter, the radius is larger here, and the image will become like this. It also is degraded. Okay, smooth this original image, and then every image pass through the Butterworth low-pass filter, and with different radius you can compare. So the result will become like this. You have a larger radius, you remain more energy, more frequency spectrum of your original image, and the image content, the degradation model, the bird effect is less. So you can see it becomes small mean square error. So this is larger mean square error. However, when you estimate this one, and here I forgot what I defined. Okay, the same should be the same. Okay, the inverse filter here, immediately you can see some good performance, because we assume there's no additive noise. You don't know, we just assume there's no additive noise. So the mean square error, okay, the same. They're getting smaller, because you remove the version of the bird error, the Butter Lopez filter error. Okay, so it's improved, becomes smaller, and you can compare what's the result. So it's getting clear. Okay, so it's no active noise. It's good. However, most of the time, our image maybe contains some active noise in different location, different position. If you still keep the same way to do it, and here we just assume there's again, okay, it's uniform blurring function. It's just uniform, like a box filter to blur this original image. Okay, and we have additive noise here. Just add some Gaussian noise with some variance. So you add Gaussian noise to this image, and we also have some protection of the inverse filter when it's more than 0.01. Don't care. Okay, but what's the result? You will see. Okay, so it's different variance of the Gaussian noise. So it's for sigma 0.03, 0.01, or should be not in the right order. Okay, good order. So 001 is the smallest one. So the active noise, we have different active noise. This is the largest one. Okay. So when sigma is the standard deviation, right? Sigma is larger, which means your bell shape is wider, and sigma is smaller when your bell shape is narrower. Okay, so this one is the most larger than compared to these two. So which means that the bell is fat. Okay, it's wider than the next two. This is the thinnest, the smallest bell shape. Okay, so we will apply this one and use inverse filter. Use inverse filter. Previously, you see, if there's no active noise, it was good. You just apply the inverse filter directly to this degraded image, and the mean square error, okay, get improved, become smaller. All good condition in different blurring mask size. Now, if we do some active noise there with different sigma, different size of noise there, and the result, even we have the protection, but the result become getting worse. Okay, only you look at the image here, disaster. Okay, you can see the high frequency spectrum was magnified. Even you have protection here, but the result is even worse than this previous original degraded image with Gaussian noise. Okay, this is degradation of the motion blur and Gaussian noise, but the inverse filter will cause this result. So you can see if you have some active noise, small active noise, the result just getting worse and worse. So what does this mean? Because your noise are distributed in all the spectrum. Okay, even the Gaussian noise, Gaussian noise, uniform noise, everywhere you have a noise spectrum, and your inverse filter will magnify the noise, especially in the high frequency domain. In the high frequency domain, it's the inverse with the small one and will be amplified. The noise energy will be amplified. So it's the result for the edge. For the noise active noise was amplified. Okay, so what's this? This one is another example for restoring image of the using the full filter and different radius of the H filter again. So you can do some modification like this one. I'm not going to inverse this filter in every spectrum. I'm going to not also the value of the HUV, but also the size of the HUV with the H cutoff value with different residue. So you can see this one is use inverse filter, full filter directly. So if you go back to look our previous example, this is what's the noise? This is a satellite image noise, right? Your atmospheric, your satellite image from this space environment, you get this Gaussian degradation model. And we just mentioned in the morning, in previous hours, we say the K is different depending on the weather condition. And if the K is like this one, unfortunately, you just have learned the inverse filter. And you know it's a Gaussian, look like a degradation. And I just do the inverse. But however, something is will occur like this one. So you have a blur image, but after your inverse filter, it becomes disaster. You see nothing. But if you change some radius, just do some small modification technique, like we use only part of the radius. So like 40, 70, 85. I don't know which one is the good. So you can see B is 40, the radius. This is 70. This is 85. So you can see there's no specific trend when your size is smaller or your size is larger, but you have to try and error for this kind of result. Okay, so this is just give you an example. If I choose different radius of the inverse filter, and the result like this one. So in this condition, they just suggest that 70 was the best one to approach to the MSE's approach to your original image as the best one. Okay, so you can see there are a lot of limitation and a lot of bad condition when you apply the inverse filter. So we try to say maybe there's some another approach. Not only depend on your filter and inverse operation. We try to do some modification and consider maybe there's some possible additive noise. Even you don't know, that's fine. We just assume, and then we know there's additive noise, and we can do some protection. And then the first one is the winner filter. Okay, the winner filter is we will introduce all the process later. Maybe not today is not enough time. Okay, just give you some idea. The result will be look like this model. So the error measure is defined as this one. So we always define your result, mean square error. So your image and your estimate image. Okay, after your process, either you use winner filter, use inverse filter, the estimate image one by one, and take the expectation value, just like the average value, and you can see how it's good. Actually, for the winner filter, the design will be look like this. What's this? If you look at this one, it's estimated UV. Your estimate new image is look like this one. So what do you have to know? What do you have to know? So here you know the GUV, definitely you got this image just transform into spectrum, and you are going to assume what kind of degradation model, and also you have to know there's an item here. What's the item? There's a very important item here. This is the spectrum of your eta, spectrum of your noise, additive noise, spectrum of your original image. And to tell the truth, I don't know what's the value there. I don't know what's the number there. But there must be some spatial ratio existed in this kind of degradation model, active noise model. So in our previous example, we assume there's no active noise. We assume, but there maybe exist. We assume there's no active noise. So what do? You just assume eta is 0, right? You assume eta is 0. So what's the result? Eta is 0, there's nothing here, and this is cancel out, become 1, and it's become inverse filter, right? Exactly, go back inverse, but now we add this content here. So the good way is we add this content there because we assume there may be some active noise existed in this degraded image. So we just add some small value here. Depends on your assumption there. Okay, so here is the value. We call it maybe I use gamma there. Okay, gamma or low tonometer there. So you put some value there, not much, at least some expected value there. We call it actually we can do some experiment to test, and actually it works. It's work. And how you do this one? How you assume this one? So we are come up some optimization problem. We are going to have some constraint condition and some target function to minimize. So after that, we can pop out there's some value existed here, and then you put that value there. It's not become inverse filter anymore. So you can see if there is small eta, and compared to this one, so it's a very small one, and it protect your noise be heavily destroyed. So this is all the process. So this is the example here. We just say we are going to find out how can I define this filter. How can I use optimization algorithm to do this one? So that's the later one we are going to demonstrate. Let me define the signal noise ratio first, and we will finish today's talk. So how can you measure it one? Okay, so the signal noise ratio is the way you to evaluate what's the result. So it's a signal noise ratio is your in frequency domain, take the square absolute value and then take a square, sum of together is a signal energy. Noise is your noise spectrum, and then take the square of the noise spectrum value energy, and then sum up together, take the ratio, we call it signal noise ratio. But in spatial domain, sorry, it's should be here. The spatial domain, you are going to calculate mean square error. It's a way to evaluate what's the differences between your estimated and your original image. So it's just take the differences and take square, sum up, take the average. We call it mean square error. And the signal noise value is just take the what? Take this like the mean square error. This is the estimate result. You estimate this result in the from your displayed image, take the square in every estimated value and in spatial domain and divide by the mean square error there. So it's a signal noise ratio in spatial domain. So you can calculate this as your measurement. And how we do that one? So this is the final result. Actually, we do for this like a winner parametric winner filter. You can see there's some constant over there. It's not exactly inverse filter, but they pop up some value there. Why we can do that one? The result is much better. We will not like this one inverse filter. It becomes like this, much better. This is a winter filter result. And you can use different, like a different radial limited inverse result and even better condition. So you have to compare. Is the right image is better than the middle one? I don't know. It's based on your visual feeling. I don't know. It should be right. It's the right one, the winner filter, and this is the inverse filter with some limitation radius, and this one should be better, right? So we will see how can we derive this winner filter, but before we go there, you need to know some matrix differentiation, mathematically. So it's different from our scalar calculus. It's a vector. So if you have time, go back to take a look first, and then next hour we are going to demonstrate how to get this winner filter with parametric parameter there, and then you can get a better result compared to the inverse filter. So that's today's talk. Stop here.